the last kind of density that we're going to talk about is a conditional density. And conditional densities describe one variable within levels or strata of others. So let's go back to our population data set, our tiny population data set here. And what we're asking about is the probabilities of age within the males. So if we first filter sex equals m, and then we count age, and then we get the relative probabilities, that's what this is tabulating here. So for age equals 1, then this is among y equals m, right? So I've grayed out the f's over here. I'm only considering the subpopulation where sex equals m, and then I'm tabulating age. So for age is 1, we have 2 out of 8. Not out of 10, because it's not the whole population, it's just the subpopulation, so it's 2 out of 8. Similarly, for ages 2 is 3 out of 8, and so on. So this is what is called the conditional density of x among those, or in the subpopulation where y equals m. So this is the notation we use here. Again, this is like the thing next to the f is like, well, f is saying this is a density, okay? And then the thing down here is the density of what? Again, all this is notation, this is convention. Sometimes you'll just see f where this stuff is clear from context, right? Or sometimes you won't. I'll talk a little bit more about this later. So that is telling you this is the density function of what. So this tells you like what table to imagine in your head. And then this tells you what is the argument. So at what age? So little x here represents either the value 1, 2, or 3. Okay. We could do the same thing the other way around. So we could ask about a subpopulation defined in terms of age, and then ask about sex. So if I filter this population to be age equals 1, and then I just count how many people are F versus M, the thing I get is this. So here for age equals 1, there's 2 males and 1 female out of the 3. And again, notationally, I would put it like this. So this is the density of Y given, or in the subpopulation where X is 1. And then we're asking about that at either the value little y equals F or at M. So this is the same thing, but I'm showing you it in an example with a much larger population data set where I can't do this by hand, but I've created this in R. I have my 5 million rows over here of age and sex. And the same code that I was using before, where I'm just filtering to a particular subpopulation and then counting on another variable, and then taking the dividing by the total number in that subpopulation, that gives me the conditional density. Like marginal densities, you can get conditional densities from joint densities. So I don't have to actually have the whole population data set to be able to compute this. I just need the joint density to be able to compute this. And the reason is very similar because as in the marginal case, because the joint density is kind of like the pre-counted version of the population data set within groups. So for example, if I want to know here, in the subpopulation of males, what is the, so this is, in the subpopulation of males, what's the probability that, or the value of the density where age equals 2? So if I wanted to get that from the joint density, what I would need to do is first look at just the males, right? So so here the answer I get, by the way, is 0.2. So if I look at the joint density and just look at the males, that's these rows here, right? And I want to know what is the total count of those, right? So the total count in that case would be 5 plus 1 plus 15 is 30 plus 15, 45 plus 5. Okay, so 50% of people are male. What percentage of people are 2 and male? So that's just this row here, right? So that is 0.1, 10%. So the percentage of people who are 2 and male relative to the total who are male is 0.1 divided by 0.5, 1/5, which is the same as 0.2. So that gives us this formula here, which I'm showing you in code, which is that if I want to get a conditional density from a joint density, if I have this joint density as this table here, what I need to do is filter by the subpopulation that I'm interested in. And then to compute the value of the conditional density, I need to take the corresponding value of the joint density. So here is, age equals 2. And you could imagine there's a imaginary column here that says sex, but it's m, right? So the 2m corresponds to the 2m here. So I'm taking that value, which is that 0.1. And what I'm dividing it by is the sum of all of these, all of these values in here. So I have my fxy would be the table where we have this column, or this row, this row, this row, this row, this row. I'm summing together those values, and then I'm dividing each of these values by the sum of those values. And that is what gives me this over here. So maybe to be clear, I should kind of make this into 2 steps. Let's just do that. If you already understand, feel free to skip ahead, but I want to make this clear. So step 1 is kind of just the filter, which would give me a table that looks like age and sex and fxy, the value of the joint density. So I have 1, 2, 3, 4, 5. My sex is all m. And then my values here are 0.05, 0.1, 0.15, 0.15, and 0.05. Okay, so this is after doing the filter. And then what I'm doing, the next step is the mutate. And what that's doing is taking all of those numbers and then adding them up. So this is the sum of all those numbers, gives you 0.5. That's what this thing is here. And I'm dividing each of them by 0.5. So 0.05 divided by 0.5 is 0.1. Like it's 5 over 50, basically, right? And so on and so forth. 1 over 5 is 0.2. 15 divided by 50 is 0.3. And then 0.05 divided by 0.5 is 0.1. So, right. So notice this number is the same as this number. So this number is the same as that number, right? All of these are just being divided by the same constant, which is the sum of all of them. Another way to think of it is I'm just rescaling. I'm filtering and then I'm rescaling. And the number that I'm rescaling by is precisely the sum of all of those, of all the numbers there. And why is that? It's just the product rule from last lecture, right? So if I want, I kind of already explained this, but if I want this conditional probability, or the count in a subpopulation, well, I just need to count when that happens, when both things happen, when is this thing that I'm interested in and people in this subpopulation relative to the total number in that subpopulation. That's the definition of the conditional probability. So it gives me this. And now this may be a little surprising here, because I previously had this number when I was explaining this just now. This number here, I was telling you, was the sum of the joint probabilities, right? What am I summing over? All the different values. So here I'm fixing y. I'm fixing y. This is fixed. Let's say y equals m, right? So this is fixed, but I'm summing up over all the ages. So for example, x in 1, 2, 3, 4, 5, right? I'm summing up the value of this joint density, and that's what I'm dividing by. That's the constant that I'm dividing by. The thing is that we actually just learned that is exactly equal to the marginal density. This is the sum of the joint density across the entirety of a particular axis. So I'm summing out all the x, and I'm left with just the marginal density of y. And this is the definition of, or one way to define the conditional density. So what we're doing here is to get the joint density. Again, remember that all we're doing is taking a subset of the joint density. So I'm filtering out just those values of the joint density table where sex equals m, for example. And then I need to rescale it so that I'm dividing all of these numbers by the sum of all of them together. And that's what this is. So the thing that you should kind of keep in your head here is that like the general shape of this should mimic the general shape of this. So here we have low value and then higher, 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 and then low again. We have low value, higher, 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 and then lower. Because this is just scaled down or up. So another way to think about what's happening here is that these numbers have to add up to 1. Because if I'm asking about the total probability that somebody is any age among males, that total probability has to be 1, right? What's the probability that anyone is between is any age in this population? We know that has to be 1. But if I add up all these numbers, it's not 1. If I add up these numbers, that corresponds to exactly what is the marginal probability that somebody is male. And so in order for all these numbers to add up to 1, we need to divide them by some scaling factor. And the scaling factor is precisely going to be the value, the marginal probability here. Okay, so a little bit of a notation here. I've actually already been in some of the slides before I wrote it in this way, and some of the slides before I wrote it in this way. The conditional density there. So let me explain what I mean here. So here, let's look at the right-hand side first. Let's say I want in the subpopulation where y equals little y, what's the density of x? I can do that for the 2 different values of little y. So let's say for x, for little y is sex, little y equals m. What's the density of age? And then what's the density of age where sex equals f? So I get these 2 different tables, okay, which represent the conditional densities of x given y equals m and x given y equals f. And all I need to do is I need to change what sex is here in the code from m to f, and that gives me one table or the other. But instead of doing that separately, one's for m and one's for f, I can do it kind of together. I can do the same thing in one operation by first grouping by sex. So now when I do the count of age is within buckets of sex. And what I get if I run this code is this table down here, which you will notice is actually exactly the same as these tables. They're just stacked one on top of each other. And this table here, I've gotten rid of the sex column because I'm labeling it outside of the table. I know that this is the density of age within the population of males. This is the density within the population of females. So each of these is a well-defined density. When I write it like this in this table, what I'm getting if I say, well, give me the conditional density of age given sex is f. First, I need to come and subset to this table, right? Or say, find me where sex is f, and then age is 2. But this total table is not a density. It's actually it's 2 densities because these numbers don't all add up to 1, right? These numbers do, and these numbers do. And so what I'm showing you in this notation up here is that this notation kind of refers to this table, and this notation refers to this table. So when I say the density of x in the subpopulation of y equals y at x, this is in fact a density. But when I write it like this is actually not a conditional density. This is kind of like a conditional density stacked on top of each other. And once you put y in here, once you fix what y is, then as a function of x, this is a conditional density. So it's a little bit of a notational trickery, kind of subtle. Hopefully that makes sense to you. It's not really a big conceptual issue. I'm just trying to explain why sometimes you'll see this notation, where really, this one is more concrete, I think. Okay, let's go back to this problem again. So same table. And now what we're doing is calculating the conditional density of child's education given that mother's education is 1, and also for mother's education is 4. Let's start with that. So given mother's education is 1, so we're asking about just these guys. So what we need to do is take all of these, add them together, and then divide them by the total. So we already calculated the total. The total of all these, I think this was 30, 46, 52, right? So if we take each of these and just divide them by that, I'm not going to actually do it. So I'm dividing by 0.52, so roughly that should be doubling these numbers. So the first one will be like roughly 32%. This will be roughly, 36, 24, and 12, roughly. That's what these numbers should be. Now we're doing the same for mother's education, so same thing down here. I need to scale these by their sum. So the sum of them is 5.5, 0.55. So if I divide those all by 0.055, and so on. And that's it. So roughly that's like going to be, for example, here, it's 1 out of 5.5. So that's going to be roughly 1 out of 5, or like 0.2. It's going to be what this is, and so on and so forth. And this is going to be like double that, so that's going to be like roughly 0.4. You can do it exactly if you want, but I'm just showing you what's going on. Here, this is, like I said before, doubling that, so 0.32, 0.36, right? 0.24. These are rough numbers, right? Don't take these literally. Okay, so what now the next question is, do they make sense to you? So again, what do these numbers represent? These numbers here represent in the population where mothers have no high school education, what is the distribution of childhood education? And we see that it's highly skewed towards low education. Whereas in the population of where mothers have graduate school education, what is the distribution of childhood education? And it's still skewed towards less education, but not nearly as much, right? So this is so here, for example, if you compare not finishing high school to grad school, it's like 3 to 1, whereas in this population, it's only 2 to 1. So that makes sense to me. Next, we're calculating a specific probability. So we want to do this using both the joint and marginal densities. So we can do this. Let's first do it with the joint density. So if we're doing this with the joint density, we want to get the cases where y is greater than 2. So that's these numbers here. But we only want to consider them relative to the in the subpopulation where x is equal to 1. So that is here. Okay, so the what we have to do there is count up how many times both of these things are occurring relative to just this thing occurring. So what we're going to get, what I mean by that is, let's remember from the last lecture, we defined this kind of conditional probability is equal to the joint probability divided by this marginal probability. Okay, so if we're going to calculate this number from the joint distribution, we need to calculate this probability, okay, and then calculate the marginal and divide the two. So if we're doing it from the joint, that's going to be this number here is going to be 0.12 plus 0.06, which is 0.18. And then what is this marginal probability? Well, we actually already calculated that. It's over here. That divided by 0.52. Okay. So you can do the math, but it's like roughly 2/5, right? Roughly 2/5. And now, I guess a little bit less than that. Now I want to use the, here this should say conditional. I want to use the conditional density directly. So I already have the conditional density directly, which is I have this number and then this number. All I need to do from the conditional density to get probability y is greater than 2, I just need to add up the conditional density at those values where y is greater than 2, right? So let's do that. So the probability that y is greater than 2 given x equals 1, I can get that from adding up the conditional density of y given x equals 1, little y. I just need to sum over values little y where they are greater than 2. So specifically, y equals 3 and y equals 4, right? So that's going to be y given x equals 1 evaluated at 3 plus the same evaluated, so I'm just going to abbreviate that, sorry, at 4. And what are these values? It's what we have here. This one is going to be 0.12 over 0.52 plus 0.06 divided by 0.52. And what does that give us? Exactly 0.18 over 0.52. Again, a little bit less than 2/5, exactly the same number that we got over here. So what I'm trying to show you is that if we already have calculated this joint density, it's a lot easier to just add these two numbers than to go back, compute the values of the joint divided by the marginal. But it's all exactly the same thing. All we're doing is just counting. We're just counting we just have different things that we've pre-counted. So either we've pre-counted certain sums in a subpopulation, or we've pre-counted sums in the total population, and then in the kind of marginal sums. So that's it. But it all comes out to the same thing. So you should be able to reason about this rather than remember specific formulas. You should be able to reason about these things by just thinking about counting people and what subpopulation do you need to count in, who do you need to exclude, that kind of stuff, rather than memorizing particular formulas about marginal and conditional densities. Okay, so we've talked about conditional densities for discrete random variables. Of course, they can also exist for continuous random variables, and it's the same intuition. If what you're doing for a discrete random variable is just taking all the values of the joint density along, in a particular place, like along an axis, and then you're scaling them all up by the same number. That's the same thing that we're doing here. So if we have, this is the joint density of x and y, and these are the values at y is a particular value. So let's say, here y is like 1, right? What are the values of the joint density as I vary x, but I keep y fixed to 1? If I look at the conditional density, it's exactly this curve. I've just taken this. It's like I'm standing over here and I'm looking at it this way. I've taken this and I've drawn that over here. The only thing is I need to scale it up because the total area under this curve will not be equal to 1, because the volume of this entire thing, the volume under this entire curve is equal to 1. So this is going to be much less. So I need to scale it up. The exact amount I need to scale it up by is the area under the curve right now, because that's, if I take this total thing, this total area, and I scale it by that, then the total area will be 1. And what is the area under this curve? That's precisely the value of the marginal density at y, which is what's shown over here. Again, if you don't totally follow that, that's okay for the continuous random variables. It's a little bit trickier because you need to do the integral, so it's not ever going to be totally rigorous in your mind. But the outcome of all of this is the same, which is that the conditional density is defined as the ratio of the joint density and the marginal, and you can still think of this as kind of like a relative probability in a subpopulation.